Hey everybody, and welcome back to the channel. We are going to do our culminating section right here, all about chemical equations. So we're going to talk about balancing chemical equations and predicting the products for chemical equations as well. And also writing word equations using the naming techniques that we just went over in the previous video. So there's a lot of stuff to this. This kind of culminates everything that we learned over in Chem 1. It puts it all together. Let's talk about what chemical equations are just to start off. So a chemical equation, of course, represents a chemical change by showing the chemical formulas of substances that are reacting and the substances that are produced. So we're showing using arrows and using plus signs and a couple of other things, what are the reactants in a particular equation and what are we producing when we combine those reactants together. So a very basic chemical equation is this that's listed right here on the screen. So I have hydrogen and nitrogen combining to form ammonia, which is NH3. And there are a lot of exceptions in chemistry, but this is not one of them. Your reactants will always be present on the left side of the arrow, and your products will always be listed on the right side of your arrow. In chemistry, you're going to see that, oh, well, this is true all of the time, except this time right here. This is always true, and it doesn't matter how many of each reactant and product you have. Reactants are always on the left side of the arrow, and your products are always on the right side of the arrow, which of course we can represent like this. So I went ahead and I just kind of underlined those on the paper so you have that down. However, when we look at this equation, this particular equation is not balanced. This equation does not satisfy the law of conservation of mass. The number of hydrogen atoms that are in your reactant side are not equal to the number of hydrogen atoms that are on your product side. You have to have the same number and type of atoms present in your reactants and your products. I can't create a hydrogen atom out of nowhere. In the same way, I can't lose a nitrogen in this process. So we have to do something that's known as balancing this equation. And we balance equations by making sure that the number and type of each atom is the exact same on both sides by adding coefficients to the front of each of my formulas. So of course, if we take a look at reactants and products again, sometimes it helps students to visualize these. So I went ahead and I made some pictures for you to look at. So that orange species right there would represent your hydrogen. And you also have a nitrogen molecule right there. However, the number and type of atoms, like we said, are not the same. I have one nitrogen that needs to be present on this side, but I need an additional hydrogen, so it doesn't add up. What we can do, like we said, is add coefficients, and coefficients are those numbers to the front of each of those formulas. So in order to balance this equation, what you can do is we can add another ammonia molecule, because 1 and 2 molecule, this can split up into its atoms and produce 2 NH3 molecules. And we represent that by putting coefficients in the front. So these are our coefficients that are now in bold and in red. So 1 and 2 molecule will produce 2 NH3 molecules. Now that still leaves our hydrogens unbalanced, but now I could easily put a coefficient in front of H2. So on my product side, if I have two groups of 3 hydrogen atoms, so 1, 2, 3, 4, 5, 6, 2 times 3 is 6, how many hydrogen molecules do I have to have on my reactant side? How many groups of 2 gives you 6? Hopefully, you would say 3. So therefore, you would have to put a coefficient of 3 in front of H2. So 3 hydrogen molecules reacts with one nitrogen molecule to produce two molecules of NH3. This is also true with the number of moles. So 3 moles of hydrogen reacts with 1 mole of nitrogen to produce 2 moles of ammonia. And that's actually the concept that we're going to use when we start our first new unit all about stoichiometry. Let's go ahead and do sample problem 10. So let's go ahead and balance each of these chemical equations together. So just like what we've been doing, we're going to do some of these together, and then I will kind of set you free to do some of these other ones. And again, by all means, if you are good at this, then you can just kind of move past this and even just check your answers. And if you get one wrong, just watch that particular section on how to fix it. So the whole point of balancing is to satisfy the law of conservation of mass. We need to make sure that the number and type of each type of atom is the same on both sides. So if we start off by looking at A, I have 2 chlorine atoms in my products, but I only have 1 chlorine atom in my reactants. So what I need to do is to add a coefficient of 2 in front of HCl. So 2 hydrochloric acid molecules will produce 1 ZnCl2 molecule. So you're only adding these coefficients or those numbers to the front. And what I like to do when I'm balancing is once I've balanced something, I like to put a little check mark above it, just so that way I know I can't change that coefficient in the front. I've already balanced it. I don't have to go back and double check the number of chlorines. Now that we've balanced chlorine, though, let's go ahead and look at hydrogen, because hydrogen is also in this molecule. So I have 2 HCl molecules. Now, technically, there's a subscript of 1 after hydrogen. So 2 groups of 1 gives me 2 hydrogen atoms, which means I have to have 2 hydrogen atoms in my product. And if I look, I do, actually. So I'm going to throw a coefficient of 1 in front of hydrogen. Now, I like to put 1s. To me, it looks more finished that way. You don't have to put 1s, but I think that when I do that personally, I see like, okay, well, I did that one already. I can't go back and change it, if that makes any sense. Let's go ahead and balance zinc and sulfurs next. So I have zinc right here, and notice there's only 1 because there's no value there, so you can assume that there is only 1 zinc atom. And I have only 1 zinc atom here as well. 1 group of 1, of course, is 1. So I'm going to throw a coefficient of 1 in front of ZnS. And let's just double check sulfur. Even though I already have coefficients in front of every single one of these reactants and products, you always want to double check. So I do in fact have 1 sulfur, 1 group of 1 is 1. And I also have 1 sulfur in my product, 1 group of 1 is 1. So this equation is now balanced. This satisfies the law of conservation of mass. The number and type of each atom is the same on both sides. Let's try B, the same exact thing. So first thing that I see is not balanced is chlorine. And as you start doing these yourself, you'll start to find your own method of doing these. So I'm going to balance chlorine first. I have 2 chlorine atoms in my products. I do need to have 2 chlorine atoms in my reactants. So I'm going to add a coefficient of 2 in front of HCl. And remember, I like to put a 1 in front of those species that I have already balanced, because in my mind, I see, okay, well, I've already tackled that element, or tackled that molecule, so I won't go back and fix that. And then, of course, I checked off my chlorine in the front. 2 hydrogen atoms in my reactants, which means I have to have 2 in my products, and I do. So I'm just going to put a coefficient of 1 there. Check that off. Let's check for chromium last. And here's another one of my kind of tips and tricks. Anytime you see something that's completely by itself, even when it's not a diatomic, especially when it's not a diatomic, balance that last. So I have one chromium atom in my products. One group of one is one, which means I must also have one in my reactants. This equation is balanced. Try C on your own. Go ahead and do that one. I think you'll find that one relatively easy as well. And you should have 1, 4, 1, 2 as your coefficients. Here's another one of my tips and tricks. So when I take a look at D, it's like, oh God, this looks really scary because there are a lot of subscripts. I have a 3 and a 4 and a 2 and a 3, and oh my God, it looks confusing. When in fact, try to narrow this down. So try to balance those elements that are in compounds first. So notice that I have an iron right here totally isolated, and I also have an aluminum here totally isolated. So try to do those last, and you'll find that they'll be easier to balance. So I'm going to balance oxygen first. So I have 4 and 3. Least common multiple of 4 and 3 is 12. So I want to get 12 oxygen atoms in the reactant side and also in the product side. Well, 3 groups of 4 is going to give me 12 oxygen atoms. And also 4 groups of 3 is going to give me 12 oxygen atoms. So I'm getting to 12 on both sides. And because I did that, it actually makes the last part of it pretty easy to balance, because look, 3 groups of 3 irons looks like I should have 9 iron atoms in my products. And if I check my aluminums, 4 groups of 2, I should have 8 aluminum atoms in my reactants. So anytime you see an element that's not bonded or it's by itself and it's not as a diatomic, just leave it and balance those last. Try to do E. E should be easy. And hopefully you saw that your coefficient should be 1, 1, 2 going across. F is interesting, and I say that because you have oxygen in 2 of your products, or in both of your products, I should say. I have oxygen here and I have oxygen here. So we have to take that into consideration when we are balancing this one. We have to take that into consideration when we are balancing with oxygen. So what I'm going to try to balance first is, I think I might try to do sulfur first. Personally, I would try to save oxygen for last, just because you have to try to balance everything prior to that. And it looks like iron is already balanced. So let's try sulfur first. I have 3 sulfur atoms in my reactants, and I have 1 in the products. So I'm going to throw a 3 in front of SO2, and I'll put a 1 in front of iron 3 sulfide. So sulfurs are now balanced. Let's double check iron. Now, because I did put a 1 in front of my reactant here that contains iron, so that one I've already solidified to be 1. That must mean I must also have 1 of that product. Now let's go ahead and check for oxygen. So you have to consider that you have oxygen in both of your products. So I have 3 oxygens in this first product, and I have 6 oxygens in this second product. So when you find the total number for here, because there's oxygen in both products, you have to consider that and balance them accordingly. So I have 3 plus 6 gives me 9. Well, this comes in pairs, and 9 divided by 2 is 4.5. So guess what? You can't have a half of a molecule. When this happens, if you happen to get a half of a molecule, what I highly recommend doing is multiplying everything by 2. Multiply every coefficient by 2 in your formula. So 1 times 2 is 2. 4.5 times 2 is 9. 1 times 2 is 2. And 3 times 2 is 6. What that does is it gets rid of that decimal. It gets rid of that fraction. When you are balancing equations, you always want to have whole numbers. And by multiplying all of those coefficients by 2, including the half, you get rid of that half, so you have all whole numbers. Let's try G. So again, I notice with G that I have oxygen in both of my products here. So I'm going to save that one for last. Looks like nitrogen's already balanced, so I'm also going to save that one for a little bit later. Let's start off with hydrogen. So I have 3 hydrogens in my reactants, and I have 2 in my products. Least common multiple is going to be 6. So I'm going to put a 3 here. 3 groups of 2 is 6. And I have 2 groups of 3 is also 6. So I'm going to cross off, or I'm going to check off my hydrogen there because I know that that is done. Let's check nitrogens now. So I have 2 nitrogens in my reactants. I need 2 in my products. Okay, I'll put a 2 there. Let's check oxygens. 2 groups of 1 is 2 oxygens plus 3 in my 3 water molecules gives me 5. So watch this. Again, I get 2 and a half. I get a half here. When you get a half of a molecule, because that can't exist, take everything and multiply it by 2. So double it all. 2 times 2 is 4. 2 and a half times 2 is 5. 2 times 2 is 4. And 3 times 2 is 6. That's an easy hack, I'll say, in order to get everything to be a whole number. Try to do H. This one's a doozy because you have hydrogen in all but one reactant and product. So when I went ahead and I balanced this, I went straight for the chlorines because I noticed that chlorine is not balanced. And personally, I like to save oxygens and hydrogens for last. So I balanced chlorines first, which means I had to double this coefficient here and then leave this coefficient as a 1. Once I did that, I can now balance nitrogens. So I need to have 2 nitrogens in my products to match the 2 in my reactants. And because I balance chlorine, I can then balance barium. So there's a 1 here. Always check those oxygens and hydrogens. They're usually the trickiest. So I have 2 oxygens here in this reactant side, which means I need to have 2 in my products, and I do right here. Don't forget to check for hydrogen. So here's where it gets tricky. 2 groups of 2 hydrogens is 8 total. But I also have 2 hydrogens in barium hydroxide. So I have 10 total hydrogens to have that I have in my reactants, which means I must have 10 hydrogens in my products. There's none here. 2 groups of 3 gives me 6. Plus 2 groups of 2 is 4. Also gives me a total of 10 hydrogens. I think the key for balancing equations is practice, because as you practice, you'll start to come up with your own method of balancing, which is really the most important. You can watch me balance all day long, and I could tell you my tips and tricks, but it's best to do these on your own and to come up with your own tips and tricks that work best for you. I do have a very lengthy balancing sheet for you to check out with lots and lots and lots of balancing. So try those out, check your answers with mine, and without further ado, let's get into the types of chemical reactions.